where we talked last time. So I'm looking at another method of bias reduction, and the method is, it is done now the following way. We are trying to create a linear combination of several plug-in estimators, okay, of our functional at unknown parameter, and we are trying to choose the sample sizes and the coefficients in such a way that the biases of individual plug-in estimator will kind of cancel out, and we will reduce the bias this way. So that's the idea. It's not always easy to show that this would work for arbitrary estimators, but if your estimator is a sample mean and you are trying to estimate the value of the functional on the expectation, it becomes easy in a way, okay, to justify it, okay, and the way to do it is just to prove to show the following simple property of the bias of this plug-in estimator based on the sample mean, right? That for smooth enough function, it will satisfy the following. The following formula will hold, okay? And in this formula, there is some remainder that is bounded this way. So there is a power already, high enough power, if we have enough smoothness of the deviation of the sample mean from the expectation. So it's a kind of, we could hope that this will be small, okay? And then the main part is certain sum in which we have powers of the sample sizes, but the coefficient do not depend on the sample size any longer, okay? The coefficient depend on the underlying distribution, depends on the functional, but do not depend on the sample sizes, okay? This is the key observation here. And then, we kind of already discussed it last time. We can choose the coefficient of this linear combination this way. We want them to satisfy this equation. So we have k equations here, and we want the first equation is the sum of the coefficients is equal to 1, and the rest are, kind of orthogonality conditions, if you wish, okay? And then this system of linear equation has unique solution, and the solution is given by these formulas, okay? These are the coefficients that we want to use. The sample sizes are all different, and moreover, we want kind of to choose the sample sizes in such a way that the difference between the two consecutive sample sizes will be more or less of the same order as n. And all sample sizes are comparable with n up to some constant that depends only on the number k, okay? And if we do this, then we will have this condition at the end, because the coefficients themselves will be bounded by constant in this case, okay? Will be bounded by constant because the product downstairs will be proportional to n to some power, and upstairs also proportional to n to some power, okay? The same power, okay? So the n will cancel out and we will be left with a constant, okay? So this is what we want. These are the assumptions that we impose on this method, okay? And then I already showed that it's easy to prove that the bias of this estimators that we created by looking at the linear combination of these plug-in estimators will be bounded just by this term, which is higher order, okay? Which is higher order already, and this is what we need. Okay, so now this is again the argument that shows this at all based on using this decomposition that I stated, right? And using the fact that we chose the coefficients and sample sizes in convenient way so that all lower order terms, right, will become zero, only remainders will survive, okay, as a result. Okay, so that's the idea behind this method. It's an old idea used in statistics for quite a while, actually, in bias reduction problems. It's also this assumption that the sum of absolute values of the coefficients is bounded by constant is also very convenient because the concentration properties of estimator we created will be just controlled by the concentration of individual plug-in estimators as a result, okay? As long as we can prove something about plug-in estimators themselves, we already know that the estimator will concentrate. So it's a rather easy method in a way to work with, to justify, say. Okay, so, you know, at this point, we just need to have for our estimator these two bounds. One bound will be on this guy, right? And another bound will also on the norm of the deviation of the sample mean from the true mean. And another bound should be proved on concentration of plug-in estimators, and then we know how the estimator behaves or obtain bounds on our estimator. Okay, I will talk about only one example in what follows. Okay, where I will apply this method, but one can apply it to any situation when these bounds are available. Okay, the same way, okay, as I will do here. Now, in statistics, people, when they do this, they usually don't do it exactly as I described by taking just linear combination of plug-in estimators. Okay, they usually transform it in what is called jackknife. Okay, estimator, and this is where it's originated. People even did not write about this. It's kind of this linear aggregation of plugins is very basic and it's important for us because in high-dimensional problems, in some sense, unless you care about efficiency, you don't need anything else. You can do this, okay? But in the traditional problems of bias reduction, it's better to do jackknife, okay? Actually, it has better asymptotic properties, okay, in a way. Okay, but in our case also, it will make sense to use jackknife because it turns out that it would allow us to produce efficiency at the end, okay? Also, it's a more complicated estimator. So what this is about? So if we consider, if I denote F sim, the sigma algebra generated by all symmetric functions of random variables y1, yn, okay, y1, yn, then I can basically project my estimator, okay, this linear combination of plugins, right? I can project it on the space of symmetric function by taking this conditional expectation, okay, with respect to sigma algebra FC. Okay, and if we have a function of m variable where m is less than n, okay, only of m variables, then the conditional expectation for these functions will be just U statistic. Okay, this is basically the way U statistics are in a way introduced. Okay, they introduced to symmetrize statistics like this. Okay, that are not symmetric, that do not depend on all variables, or they're not symmetric. Okay, that's just the way to create U statistic, okay, by this conditioning. So it means that essentially this estimator will become the sum of certain U statistics, right? And each U statistics corresponds, the kernel of each U statistics would be individual plug-in estimator, okay? It's a function of smaller number of variables, and then we create U statistic, okay? In the settings that I described, this would be computationally terrible to use this estimator because we choose the sample sizes. All sample sizes are comparable with n. So it's like you are looking at U statistics where m is comparable with n. M, say, is 1/2 of n. Okay, in this case, you will have lots of subsamples over which you have to average. Okay, so it will be computationally much worse. Okay, thing to do. Okay, but you can avoid, of course, if your purpose is to compute this thing, you can avoid doing this. You can just create, pick at random sufficient number of samples here and average only over smaller number of samples, not necessarily over all subsamples of size n. Okay, this would reduce a little bit the cost of computing this estimator, but still it will be much computationally much worse than simple aggregation of linear aggregation of plugin estimators. Okay, you will need to compute your functional of many plugin estimators. Okay, that correspond to all subsamples like this in this case. Okay, or at least to some randomly picked subsamples. Okay, so it's kind of in this type of problems, for those who, unlike me, compute these estimators, it could be a difficulty. Okay. Okay, now if this estimator, since it's defined as conditional expectation with respect to this sigma algebra of symmetric events, if you wish, okay, its expectation is the same, okay, by the properties of conditional. So bias is the same. Just creating estimator with exactly the same bias. And by properties of conditional expectation, you can see that this inequalities also hold. So it means that the concentration properties will be the same as for individual plugin estimator. Okay, individual plugin estimator. So in traditional bias reduction methods, when people choose this N1, N2, and so on, not the same way as we do, not necessarily comparable with the whole sample, okay? They usually, kind of, there is some advantage here because they are using U statistic and there is additional averaging, okay? But in this case, we're just using the fact that it's going to behave the same way, okay? Not worse than this estimator, okay? Okay, so we have the same concentration properties. So why to use it at all? The reason to use it is basically related to this property that non-symmetrized estimator is not going to possess. Okay, this property is of importance to us because it allows us to separate the term here, which is the sum of independent random variables, and this term will be asymptotically normal. As a result, okay, will be close to normal distribution. So here, as you see, we upper bound this approximation of this difference by the sum of independent random variables. We approximated, we bound it in terms of concentration of the remainders of Taylor expansion, okay? Of the remainders of Taylor expansions. And as you saw in other examples, I already considered the remainders of Taylor expansion will concentrate better than the plugin estimators themselves, okay? It will be smaller thing, okay? Smaller thing, and you will get here something of the order, say 1 over square root of n, and here something which will be a small of 1 over square root of n, so it will allow you to justify normal approximation, okay? Why this property holds? It's very easy, as everything here is easy in this analysis, unlike, this previous method that I discussed. It's very easy method to think about, okay? So if I write, our non-symmetrized estimator first, it's, kind of its deviation from its expectation. Then it can be written this way, and then we can here use Taylor expansion with remainder SF, right, in order to rewrite it in this form. Okay, in order to rewrite it in this form. So then, in order to say something about symmetrized version, we will need to take conditional expectation of both sides, right, with respect to our sigma algebra of symmetric events, okay? And a simple observation tells you that conditional expectation of the first part will be just equal to this, okay? Will be just equal to this. Why this is the case? This is the case because if you write expectation, say, of y1 of any of our variables, or yi, okay, any of our variables, right, with respect to sigma algebra F sim, so this is projection of yi on symmetric random variables, and the answer will be yn with bar. Okay, the answer will be yn with bar. That's just the property that we need to use here, and as a result, what we are getting that conditional expectation of y and j with bars, and just an average, okay, of nj copies of guys like this, also will be equal to yn with bar. So symmetrization of any sample mean corresponding to smaller sample size is the whole sample mean based on all the data, okay? That's the property we are using. And as a result, when you compute this conditional expectation here, you will since the sum of the coefficients is also equal to 1, you will end up just with this term, and this is terms that allow us to achieve efficiency in this problem, okay, basically. Okay, so that's about this estimator. So now to summarize, in order to say something about these two estimators, including symmetrized, we need to have bounds on this thing, we need to know bound on this thing, right? And we need to know bound on concentration of the remainder of Taylor expansion of the first order, okay? That's all from here, all the theory of these estimators would follow, okay? Okay, so now I will start talking just about one problem, and this will be about estimation of Hölder smooth functionals of covariance, okay? Of covariance in Gaussian models, right? Using this method, we are linear aggregation of plug-in estimators. So linear aggregation of sample covariances corresponds to several sample sizes. So we will be again studying this problem in a general framework. Okay, X will be a random variable. It will be a centered random variable in a separable Banach space. In fact, we will assume always that it's a normal random variable or a Gaussian random variable in infinite dimensional spaces. We do not say normal, we say Gaussian, okay? A Gaussian random variable in our Banach space with mean 0 and covariance operator sigma. Now, what is covariance in this setting? Okay, I actually don't care that much about the space being infinite dimensional, but what I more care about is that I allow myself to use arbitrary norm. Okay, it's not necessarily Euclidean norm, so this way it covers many more situations, okay? Many more situations, so it's not necessarily Euclidean norm, it could be an arbitrary Banach norm, and then there is a dual space star, and covariance operator, it's an operator from the dual space into E that is defined by this expression, right? That is defined by this expression. In other words, covariance operator is operator whose bilinear form gives us covariance between two linear forms of xu and xv. Okay, that's what covariance operator is. Okay, it's a symmetric positively definite operator from E star into E. And in the case of Gaussian random vectors, centered Gaussian random vectors, it gives complete characterization of the distribution. Okay, as in as we do in finite dimensional cases. Okay, so now what will be our goal? We will be looking at some functionals defined on the space of symmetric bounded linear operators or some subspaces of this space, right? That act from E star into E, right? We will equip this space with the operator norm. Okay, that's the operator norm. Okay, we will equip the space at the operator with the operator norm. This would allow us to talk about Hölder smoothness of our functionals. There is underlying norm on this space. Functionals will be defined on this space L E star E, right? There is underlying smoothness and we can underlying norm, and in terms of this norm, we can define Hölder smoothness, right? Hölder smoothness, and we want to estimate f of sigma now for functional of certain smoothness based on IAD observations. Okay, based on IAD observations. Okay, so this is, I gave here a couple of examples of Gölder smooth functionals, okay? Well, which functionals will be covered by this definition? The examples will be in the case of Hilbert space, okay? In the case of Hilbert space. So in the case of Hilbert space, covariance operator is, Hilbert space is equal to its dual. So covariance operator will be self-adjoint operator, right, in acting in Hilbert space. So we have the space of self-adjoint operators equipped with the operator norm. Then the most natural probably example of a function of operator, okay, not even real valued functional, but of a mapping, right, that maps operators to operators, that is commonly used, would be this mapping, okay? We can start with a function of real variable, and any such functions induces in a standard way via spectral theorem, okay? Via spectral theorem induces functions on operators, okay? Acting on operators, so on matrices, right? That's a standard thing, okay? So this, as those of you who studied functional analysis, some functional analysis operator theory know that since at least von Neumann, okay, it's known how to do it, even in infinite dimensional spaces, okay? But since we will deal only with covariance operators and they are compact, okay, it's kind of even easier in this case, because if we have our self-adjoint compact operator, it has a kind of discrete spectrum and has this type of spectral decomposition with eigenvalues lambda and spectral projections p lambda, okay? Spectral projections p lambda. Then the function and the operator functions induced by real function of real variable g will be just operator g of a defined by this expression, right? This is how we apply functions to matrices, right? This is what is for matrices a square, a cube, or e to the power a, or sine of a, okay? Okay? Okay, so now, of course, people at operator theory studied a lot the following question. If you have a function and real variable of certain smoothness, what kind of smoothness the corresponding operator function will have, okay? What kind of smoothness properties the corresponding operator function will have. And when I looked at this literature, I did not find there exactly this claim that is given here, but it was easy for me to prove it for myself, extracting necessary bounds from the literature, okay, that people wrote that if you look at such operator function G, so this is now G applied to operator, an operator function, right? Then it's Hölder norm, Hölder CS norm. If we view CS norm as a norm of functions defined on on self-adjoint operators, right? On self-adjoint operators, and we equip the space of self-adjoint operators again with the operator norm, right? So Hölder CS norm of the operator function G can be controlled in terms of certain norm on functions of real variable, and this norm is one of Bessel norms, okay? This is Bessel norm, right? B as infinity one. I'm not going to give you the definition of Besov space, but this is something, this is a slightly stronger notion of smoothness, right, than Hölder smoothness, okay, would be for real valued function. So you need to ask a bit more smoothness, right, of function of real variable in order to create Hölder smooth function of an operator, okay, of an operator. So this is one example with which we will live. And you can create a functional, for instance, by taking trace of this thing. So it will be kind of linear functional of operator function, right? And this is already real valued functional. And for this functional, of course, you will have also this bound, okay? In this case, okay? So if B is say a nuclear operator, right, a trace class operator, then we will have this type of smoothness of the function. Okay. In particular, you can think about such things as bilinear forms of operator functions like this, right? If you take bilinear form, you take say G of A and create inner product G of A U inner product with V, right? Then this would have this type of smoothness, right? This type of smoothness, and you can this way you can look at, for instance, entries entries of the matrix G of A in some base of G of A in some basis. Okay, that's something that you can look at. Okay, these things will be Hölder smooth in the sense of our definition. Okay. You can look also at these examples that actually can be in a way reduced to the previous example, okay, if you wish. You can reduce it to the previous example or view it separately. If you look at such things as spectral projections, okay, spectral projections of the operators, okay, of self-adjoint operators. For instance, you look at spectral projections that corresponds to the top eigenvalue, okay, to the top eigenvalue. Of course, it's not going to be globally smooth, but it's going to be locally smooth, okay? If you fix some, for instance, in our case, covariance operator, okay, with certain properties such that, for instance, the top eigenvalue is of multiplicity L, right? And then there is gap between the top eigenvalue, right, and the next eigenvalue, right? The next eigenvalue. So the first eigenvalue is of multiplicity L, so I wrote L eigenvalues, and then lambda L plus 1 already smaller, and there is a gap, right? There is a gap. Then if you take a neighborhood, right? A neighborhood of sigma naught, operator norm neighborhood, right? Of size delta, where delta is smaller than spectral gap divided by something, divided by 8, but probably it's enough 3 maybe, okay? But that does not matter, right? If you take neighborhood of such size, then in this neighborhood, you know, all operators in this neighborhood, they also will have top eigenvalues of multiplicity L, right? Of multiplicity L, and spectral projection will depend smoothly, okay, on A in the neighborhood like this, okay. So locally, you can kind of use this Hölder smoothness, and you will have bounds on the derivatives expressed in terms of the spectral gap in this case, okay? In terms of the spectral gap. So this is how this type of things can be used if you deal, for instance, with such things as principal components. You know, in principal component analysis is kind of where this machinery could be used, okay? Yep.
In infinite dimensional spaces, you may not have a spectral gap, right?
Sorry?
In infinite dimensional spaces, you may not have.
Well, yeah, but we are talking about compact operators. Okay, with this, the spectrum is discrete, so yeah, it's yeah. I'm talking about covariance operators. They are always compact. Okay. Okay. So now we can, of course, as a kind of a natural estimator of the true covariance would be the sample covariance, right? The sample covariance, it's kind of the sample mean that corresponds to the true covariance, okay? That corresponds to the true covariance. And of course, the sample covariance, you know, could be used in this functional estimation method that we discussed, okay? Because it's exactly the sample mean, so we can just work with the sample covariance. So let's discuss what are the basic properties of sample covariances in this type of situations. What is the error bound of the sample covariance and things like this. First of all, in the case when E is RD, say Euclidean space, right? These are rather common bounds, okay, that are not hard to prove, okay, and kind of are available now in various texts on high-dimensional statistics. Okay, always are given, okay, with proofs, okay, what will happen with the operator norm error. This is, we measure this error in operator norm, right? Roughly it tells that it will be of the order square root of d over n, right? There is rather nice concentration properties here also, right? And you have this kind of Bernstein type bounds, right? That hold with high probability, for instance, and you have bounds on piece moments like this, you know, so there are various tools that are available, okay? However, bounds in terms of dimension, okay, are not necessarily sharp, okay? They're going to be sharp when our sample covariance is somehow close in some sense to identity, okay? By this I mean that it has spectrum bounded away from zero, okay, by a constant. Okay, if it has spectrum bounded away from zero by a constant, it would be kind of approximately isotropic operator, okay? And in this case, everything controlled in terms of the dimension. But you can easily convince yourselves that this is not always good. If your covariance operator, for instance, if your dimension of the space is million and your covariance operator is of rank 3, right? You, of course, could write 3 in this bound rather than write million, okay? Because essentially your covariance operator will act only in a subspace, in three-dimensional subspace, and you can reduce the dimension of the space just like this, okay? But of course, covariance operators are not necessarily of rank 3. Okay, they could have even infinite rank. Okay, but still they can have eigenvalues that decay fast. Okay, and in this case we want to have some complexity parameters that would work better than dimension in this case, because dimension would be bad in such cases as well. It's kind of clear, right? So it turns out that something that I already mentioned before, the notion of effective rank, okay, effective rank of covariance operator, that we already mentioned it when we discussed Gaussian shift model in Banach spaces. We used it essentially, okay? So it's defined as the ratio of expectation of norm of x squared divided by norm of sigma. It's kind of valid definition in any Banach space, okay? In any Banach space. You can rewrite it, you know, numerator and denominator this way, right? And when it's written this way, you immediately see that effective rank will be greater or equals than 1. Okay, will be greater or equals than 1. Now, there are some other properties that I listed here. This one is kind of important because it tells that effective rank is always smaller than the rank of operator sigma, right? And the rank itself is upper bounded by the dimension of the space. Okay, so it's always better than to use dimension. Okay, to use this, and moreover, you know, if your space is infinite dimensional, effective rank is still finite. Okay, effective rank is still finite, so it's a finite quantity. And in the case when H is a Hilbert space, effective rank will be equal just to the trace of sigma divided by the operator norm of sigma. Okay, by the operator norm of sigma, since expectation of the square of the norm will be equal to the trace of sigma. Okay, And this is the case that I kind of discussed the solution of the functional estimation problem exactly under these conditions, that the spectrum is bounded away from zero and bounded from above, okay? Bounded from above. And I told you that I was not able to do anything better than this in the case because I was using this random homotopy method, okay, with the previous method, okay? And in this case, of course, the effective rank is proportional to the dimension, right? Proportional to the dimension, so there is no need to use effective rank, so it does not appear even in this situation, okay? Okay, however, in general case, effective rank, it turns out, becomes a right way to measure complexity of covariance estimation problem. Okay, it's just the right way, okay, to do it. Actually, the notion of effective rank under a different name existed in the literature long before it started being used in statistics, okay? It kind of originated in Banach spaces, literature in connection with so-called Dvoretsky theorem. Okay, Dvoretsky theorem, well-known result in the theory of Banach spaces, and this result has a kind of probabilistic proof, usually based on some concentration arguments. Okay, basically, it's the result that tells you that in Banach, in infinite dimensional Banach space, you can find subspaces where the Banach norm will be almost equivalent to Hilbert norm. Okay, so it will be almost Hilbertian subspaces, okay, of the Banach space. Okay, and if your Banach space is high dimensional, say, you can find such subspaces of sufficiently large dimension. Okay, so this was proved by Dvoretsky in the early 60s, and then there were other versions of the proof, and Pizier was working on this in the 80s and gave certain Gaussian characterization of this property, and the quantity that determines the dimension of the subspace that you can find in your Banach space was exactly the effective rank, okay, of Gaussian covariance, okay? Okay, so that's just a remark, okay, that things in this world are related one to another, okay? So closer to our problem, okay, it turns out that effective rank completely characterize always the size of the operator norm error of the sample covariance as an estimator of covariance. So up to numerical constant, the expectation of the operator norm error will look like this. So it's the same type of as upper bound in terms of dimension, right? But in terms of dimension, it's an upper bound, right? And now dimension can be replaced by effective rank, and it's also a lower bound, okay? So it's just the size of this quantity. And moreover, you can add to this rather strong concentration property of this norm around its expectation, right? And this gives you complete characterization. You will have exactly the same inequalities that I wrote in terms of dimensions that can be rewritten in terms of the effective rank. Okay, so it's true in arbitrary infinite dimensional Banach space, and even in finite dimensional spaces, it might make sense to use effective rank instead of the dimension if it's much smaller, okay, which is often the case. Okay, so that's the bounds that we will use in what follows. Now, sometimes we might need to use not the operator norm, but shortened p norms. Okay, this is defined in the case when our space is Hilbert space. Okay, is Hilbert space. So I gave these norms, of course, are defined for operators that are not necessarily self-adjoint. Okay, but we will deal only with self-adjoint operators. So this is the definition of shortened p norm, right? It's given by this trace of absolute value of the operator raised to the power p, and yeah, I think I have not written what, yes, absolute value of the operator is defined here, okay? Of course, standard. standard definition, and then we have the Schatten norm. In the case when our Hilbert space is d-dimensional, there is this straightforward upper bound, okay, on the Schatten P norm. So this is essentially matrix, right, in this case. So Schatten P norm, right, will be bounded by d to the power 1 over p times the operator norm. And if we combine this with the bound on the operator norm in terms of the dimension, we can, for instance, derive something like this, okay? Something like this, so there will be only this factor d to the power 1 over p in front. Okay, it is of interest, of course, to know whether you can replace this d here by effective rank, okay, in this bound. For Schatten norms, it turns out that something along this direction is possible. Also, I doubt that this bound that I stated here is the final result in this direction. Probably it can be written in a cleaner way, okay, but this was enough for my purposes, okay, and I used it in some papers related to functional estimation, okay. So this, you can see that basically, you know, it's kind of the same type of bound, okay, maybe better it's here, because when we are not trying to write explicitly the dependence on p, which sometimes is important, okay, so you're ending up with, instead of d to the power 1 over p, with r of sigma to the power 1 over p, right, and still have more or less the same terms. There is some term with logarithm. I'm not sure that it's needed, but it's probably related to the proof. The proof is based on so-called non-commutative Hinchian inequality, and usually when you apply this type of inequalities, you are gaining such logarithmic terms, okay? So maybe there is another proof that does not require this, okay? But it was not important for in this application that I am looking at. Okay, so what we want to do at the end, okay? Ultimately, we want to study the following problem. I will introduce here on the space of symmetric operators acting from E star to E, symmetric bounded operators. I will introduce another version of Hölderlin norm, slightly modified version of Hölderlin norm. I call it weighted Hölderlin norm. So I put some weights, okay, on the norms of the derivative, some weight A, okay. Why I am doing this, it's not for any decent reason, to be honest, okay, just because when I started in this problem studying upper and lower minimax bounds, I was able to write matching bounds using these norms, okay, so it's just more convenient way for me to write the bounds, okay? So it's a kind of a modification of the definition of Hölderlin norm. I'm using some weight A, and the same A appears here. So this is the class of covariance operators whose operator norm is bounded by A and whose effective rank is bounded by R, okay? Bounding by R. And at the end, we will try to find the size of this type quantities. I will do it locally because I don't know how to prove lower bound globally, and maybe it makes sense, okay? Because essentially, in order to estimate f of sigma, you don't need at all to know that f is smooth on the whole space. It's enough for you to have smoothness only around sigma, okay, around true parameter sigma, right? So that's there is something, some truth to this, okay, that you don't need to make the bounds global, okay. So I kind of encountered this kind of aspect of the problem in this setting, and in the case when I was looking at some local bounds, I was able to nail down the size of this quantity, okay. The size of this quantity is possible to know it precisely, okay? Well, I don't know whether I will be able to show you the main parts of the proof of this, but we will go through some details now. Okay. So the estimators I will be using are these estimators, exactly the estimators that we already discussed, okay, that we already discussed. So I'm using it in this framework Y will be X tensor product with X, okay? So I'm averaging this rank 1 operators that which gives me sample covariance, right? Expectation of X tensor product with X is the covariance, okay? So that's our setting, right? So I kind of, in this situation, I drop this hat here just to simplify notation, right? And now I view it as a function of x1, xn. Here it's written as a function of this tensor product. Okay, the function of the tensor products. But we will use all these inequalities that we discussed before in the general framework. Okay, they will be just used, okay, as they should. And there will be symmetrized version of this estimator again, which is what is called jackknife in statistics, okay? Okay, so this is one of the first results. It's a global bound, so I'm assuming some global differentiability, right? I assume that f is k times differentiable on the whole space of bounded symmetric operators, right? Bounded symmetric operators from E star into E, and the last derivative satisfies Lipschitz condition with constant rho. So we have smoothness S, which is k plus rho in this case, right? Which is k plus rho. In this case, it's possible to prove this bound, okay? To prove this bound, so you have when R of sigma is less than n, this will be just 1. So the first term is of the order 1 over square root of n, and the last term is of this order, right? You have square root of R of sigma divided by n raised to the power s, okay? So R of sigma is a substitute for dimension, okay, as it should be, right? And the bound is of the same type as what we discussed before. The same bound holds for symmetrized version of the estimator, okay, by what we discussed, okay. Now, as we saw many times, this bound tells us that there will be some phase transition in the error rates, right? When smoothness is sufficiently large, we will get 1 over square root of n rate. Otherwise, the rate will be slower, okay? Otherwise, the rate will be slower. Okay, so this is a local version of this bound, okay, which will will be used when I state this minimax result, okay, so that's this where it will be needed. So I'm assuming that that f is here, that f is differentiable, the same type of differentiability holds, but only in the neighborhood of the true covariance, right? Only in some u, right, that is around our true covariance. This is operator norm neighborhood, right? Operator norm neighborhood. And then, you know, there is more or less quite similar bound with some additional terms that kind of is related to the fact that I need now to see what will happen when my estimators, for instance, will be outside of this neighborhood, okay, which could happen easily, right? My sample covariance is outside of this neighborhood. I have to sort of add additional terms that is based on this fact that the estimator could be outside, and then I need to control probability of this, and this is this appears in this exponential stuff at the end, right? So this is, by all purposes, this is negligible term, okay? That much smaller than the rest of the bound, okay? But this is a local version of the bound. Now, this is the result that tells that for symmetrized version of the estimator, you will have approximation by these statisticians often call it linear term, right? By linear process, okay? Which is the sum of independent random variables, and we can use it now to prove Gaussian approximation, okay? For symmetrized version of the estimator to see that it's asymptotically normal and even asymptotically efficient in a way, okay? Asymptotically efficient. So this is again the same type of bounds that we saw before. We can see that we can make sure that when R of sigma is smaller than n, okay, something like a small of n, right? We will get the right hand side of the bound of the order O small of 1 over square root of n, right? And what we are using to approximate the deviation of our estimator from what we are trying to estimate is of the order 1 over square root of n, because it's controlled by the central limit 0, okay? So it's the result about, in a way, about normal approximation, okay? About normal approximation, okay. So this is what follows immediately, okay, from the result I stated, okay. These are some bounds on this type of things, right? This is Wasserstein distance between properly normalized estimator, right, and standard normal distribution, and you can easily figure out when normal approximation holds. Basically, you need to have enough smoothness, right? Enough smoothness so that this thing will become smaller than 1 over square root of n, right? So that the product will tend to 0. This is one thing, and R of sigma should be a small of n. Okay, that's what is also needed, right? In this case, you will see that the mean squared error basically will converge to this limit variance, right? And you will have also normal approximation here. Okay, so that basically what everything follows from this bound that I stated before. Okay, Okay. Yeah, so you can write when this is happening. So S should be above this threshold, the degree of smoothness where of sigma smaller than n to the power alpha. Then you have this property, right? And this first property kind of would allow you to claim that there is efficiency if we combined it with the corresponding lower bound. And we had even general version of such bound. You know, I stated it at the beginning of the course. Okay, so it's all leads to efficiency of this estimator. Okay, so this is, you know, I discussed this example of spectral projection, right? And I told that it can be viewed as a locally smooth, locally Hölder functional, right? Locally smooth functional, right? Locally smooth functional in some operator norm neighborhood, right? Operator norm neighborhood of some operator sigma naught, for which we have information about the top eigenvalues, that it has certain multiplicity, right? And there is a spectral gap after this, okay? After this. So if you look at this example, right? At this example, and use the type of bounds I stated, you can easily derive this type of bound in this case, right? This type of bound. So you can use this for any k, okay? So we don't know really for which k it's used, because it will be infinitely differentiable in this case, right? It will hold for any k. The only thing you have to have in mind here that when you are using this estimator, the constant here will typically grow exponentially with k, right? So you should not try to use it for very large k, okay? Because then you can be killed by the constant, right? So by the constant here, but basically, you know, you need to be in the situation when R is still smaller, the rank or effective rank is still smaller than n. Okay, it's not you kind of can think about the situation in this context when R is comparable with n. Okay, when R over n is some number. Okay, some number that so that this is less than 1, but then you will be forced to, in order to kill this term, okay, and to have 1 over square root of n size of error, you will be forced to choose k large, okay, and this is not that innocent as it might look, okay, because just of this simple notation and the inequality, okay? And this constant is large, okay? This is because of this choice, okay, that we are making of coefficients, actually, okay? There is some problem behind it, okay, whether there is a way to modify this estimator in such a way that you can use it for very smooth functionals, okay, like this one, okay? So that you can kill the last term without hurting too much with large constants in the bound, okay? But it's probably not for this estimation method. You will need to use different estimation method. Okay. Okay, so I will discuss very briefly some ingredients in the proof of this result, okay, in the proof of this result. So one ingredient is this bound on the bias that we already on the bias of this estimator that we already discussed, okay? In fact, I think I wrote it, it will be strictly speaking maximum of this expectation over all sample sizes Nj. So it's not correct what I wrote, okay, the way I wrote it. But since the sample sizes Nj are all comparable with that, it will be basically this, okay? Will be basically this, but it's not formally true, okay? But I should put here Nj and put maximum over Nj from j equal 1 to k, okay? But then still we are using, you are using this bound, and whether you are using it with Nj or with n, you will get the same thing, okay, as a result, okay? So that's a typo, okay, say, okay, and then we are ending up with this bound if we combine it with the bound on the expectation of the operator norm, okay? Okay, so that's how the bias is handled in these problems. And then an important ingredient is this concentration bound, okay? You need this type of concentration bounds and also concentration bounds on the remainder, okay? I'm not going to talk about concentration bounds on the remainder, but let's discuss this concentration bound. You remember at the beginning I stated you a bound on the concentration of the operator norm error of sample covariance. There was a bound on concentration of this thing. Okay, I showed that with high probability it will be bounded by some expressions that depends on the sample size and an operator norm of sigma, basically. Okay, in a weak sense depends also on effective rank. Okay, the bound was exactly of this type. Okay, and it can be derived actually from this result also. Okay, because you know, if you call this, for instance, G, if you call this thing, for instance, G of sigma n hat, right? This functional G will be Lipschitz, of course, right? And it will be Lipschitz with constant 1, right? As something that depends on sigma n hat, right? It will be Lipschitz, so you can and this is a bound for arbitrary Lipschitz functional of sigma n hat, so you can apply this inequality in order to get this bound, okay? It's written as a bound on LP norm, but this is equivalent to exponential bound. You can also say that if you instead of p you will put here t, you can say that with probability at least 1 minus e to the power minus t, this the absolute value of this thing, right? The absolute value of this thing will be smaller than this thing, and here you will have square root of t over n plus t over n. And this was exactly the bound that I stated. Okay, so it's a bound that implies this result also about concentration of the operator norm error of the sample covariance. Well, I kind of sketched here the proof of this bound, okay? So it's again the same game. It's an application of basic concentration inequality for a functional of something Gaussian in some Banach space. In this case, we need to choose the space, and the space will be kind of this cross product of n copies of E. Okay, it's kind of the space of n tuples, okay, where each coordinate belongs to E. I can equip this with norm, for instance, like this, okay, like this, and it will make it a Banach space, right? It will be a Banach space as a result. The dual space to this space will be this product, right? Will be this product, and the norm can be defined, the dual norm, okay, will be defined exactly the same way as this one, but we will need to use, we will need to square there the dual norms, right? Because it will be kind of, it will be linear functionals on E, right? The components will be linear functionals on E, so you need to square their proper norms, right? Dual norms in the dual space, okay? But it will have the same structure, right? Now, if you write our NIAD observations, we have a vector now xn that lives in this space E times E times C, right? It's a random vector in this space, and this vector is Gaussian with some covariance sigma n, and this covariance will be written this way. Okay, maybe you can better see it if I write write it as a matrix. Okay, so this will be kind of sigma, right? It's kind of a block matrix like this, right? This will be sigma n. Okay, if you wish, right? This is sigma n. Now each sigma, for instance, this sigma acts from E star, right, into E, say, right? Acts from E star into E, okay? And then the next sigma that will be here acts also from E star into E, but this will be different copies of these spaces, right? Then we create this block matrix, right? And this will be sigma n, essentially, right? But the bilinear form can be written this way then, okay? The bilinear form can be written this way. From this, it's easy to see, immediate to see that the operator norm of sigma n is the same as the operator norm of sigma. Okay, not different, it's the same. And now our sample covariance can be viewed now as something that depends on this Gaussian vector xn. Okay, because sample covariance is a function of x1, xn. Okay, so we can view it this way. And then we need to do our usual exercise. We have to bound certain local Lipschitz constants, right, in order to derive concentration inequality, right? We have to bound local Lipschitz function. So we will bound local Lipschitz constant of this function sigma n hat that depends on xn, right? And it turns out that this requires some computation, right? And then it turns out that it will be bounded by what I wrote, okay? By sigma n hat to the power of 1/2 divided by square root of n, okay? You have to, we will need also a bound for square root of norm of sigma n hat, okay, for this thing, okay? And it turns out that in this thing is just Lipschitz, right, with constant 1 over square root of n. Okay, as constant 1 over square root of n. And finally, we need it for this thing for which we want to prove concentration, right? For our functional applied to Lipschitz, functional applied to sigma n hat. And for this, it will be quite naturally just the same thing as here multiplied by the norm, Lipschitz norm of f, right? So we have this bounds, and now we can just write standard inequality. So it's a machine basically that does it for us. Okay, it can be ChatGPT can do this easily. Okay, this type of thing. Okay, it's not there is nothing intellectual here. You just need to write. You need to write bounds on this. Local Lipschitz constants, right? And then you write inequalities. This is essentially general inequality. So I put here local Lipschitz constant, and I have norm of local Lipschitz constant. It's multiplied as a general Gaussian inequalities that we have, right? And then we just replace this by the upper bound that we have, right? Replace this by the upper bound, and we end up as a result with this. So this norm sigma n hat to the power of 1/2, this is something random, And for this, we need to control the LP norm, right? LP norm. And then we basically add expectation of this thing and subtract expectation of this thing, right? And rewrite it as sum of two terms. One term will be expectation of square root of this guy, right? And another term will be LP norm of this difference, right? And as I mentioned here, this has Lipschitz, this is Lipschitz. It has Lipschitz constant 1 over square root of n. So for this, we can immediately apply again concentration inequality, right? So it's kind of iterative application of concentration inequality. Here, it's enough to use 2 iterations, right? Here we use concentration inequality again. Concentration inequality again, and as a result, then we use this kind of straightforward bounds that are available to us, right? And this is the bound on this guy, and then we plug in everything, and we are getting the inequality that I stated. Okay, so that's basically how this type of things can be proved. Okay, so it's a bit the same type of exercise, a bit more complicated. It's just to prove concentration bound on the for the remainder of the Taylor expansion. Okay, this is also something we need, and all these things together lead, plus what I discussed at the beginning about a general framework of this for these estimators. Okay. Based on aggregation of plugins, right? And this is basically what we need, okay, to prove these results. Okay. Now, let me state something that I promised at the beginning that I will state. I state here some bound on our estimator, okay? Some bound on our estimator, but I state it as a bound on supremum, okay? So here I have supremum over all sigma in certain class of covariance. This is the class of covariances whose operator norm is bounded by A and whose effective rank is bounded by R. All covariances like this. So I can put sup over this, I can put sup over all covariances from this class that are close to some sigma naught, in the neighborhood of some sigma naught. And this is where we have smoothness, right, of our functional in this neighborhood, right? And I can put supremum over all functionals for which this weighted Hölder norm is bounded by 1, so kind of Hölder ball in this norm. And as a result, I am getting just this bound in the right-hand side, 1 over square root of n plus square root of r over n to the power s. Okay, kind of standard bound that we are looking at, but now expressed in terms of the maximal effective rank in this class of covariances, right? We are working with, okay? And then the goal becomes to prove matching lower bound, okay? Matching minimax lower bound, okay, on this. Okay, and it turns out that it's possible to do, not always, okay, not always, but I was able to prove it in the case when our space is Hilbert space, okay, where E is a Hilbert space, and also under special assumptions on this operator sigma naught. So it should be in the neighborhood of some operators of special type. I call this operator, this is just due to the construction of the lower bound, okay? I call, maybe it's true in other situations too, but at least for these operators, the upper bound is sharp, okay? So I have this equivalence here, okay, in this case. So what kind of operators, sigma naught should be? I call it spiked covariance. Okay, so I call sigma naught spike covariance of rank D, for instance, right? It means that the spectrum of this covariance operator consists only of 3 eigenvalues, right? Lambda is the largest eigenvalues. It should be of multiplicity 1. Mu is the next eigenvalue. It will be of multiplicity d minus 1. And then if we are in infinite dimensional space, there is, lots of zeros, okay, after this, okay? The rest of the eigenvalues are zeros, okay? The rest of the eigenvalues are zeros. It's like one spike, okay? There is one spike corresponding to the top eigenvalue, and then the rest, it's like spike covariance model, frequently used in statistics, okay? And if you are around such operator, then you have lower bound. Here it should be spike covariance of rank, which is the integer part of number r. So basically rank r, okay? Okay, where r is the same as here, okay? Okay, so let me spend a few minutes to discuss the proof. Okay, the proof is a bit complicated. Okay, but at least I will tell you some ideas involved in this proof. Okay, it's actually heavily rely on some certain things that was done already in this very old papers written by Arkady Nemirovsky. Okay, there is some construction that is used in this proof. Okay, it's kind of useful construction in this lower bounds. Some information theoretic construction, if you wish, or coding construction. Okay, so we have sigma naught that is of this form. It's lambda multiplied by the spectral projections that correspond to the largest eigenvalue, right? This u times u will be eigenvector, okay? It corresponds to the largest eigenvalue, and then it's mu multiplied by PL minus u tensor product with u, and L is a space of dimension d. Okay, it's another way to describe what is the spike covariance. L is the subspace of dimension d. U belongs to this subspace, right? And we are dealing with operator of this form. Okay, with operator of this form. Now we can identify, and that what follows, we will do it. We can identify L with RD. Okay, L with RD. And we can actually constrain our problem to RD. Everything will be happening in the space RD. We don't care much about the rest. Okay, here. Then what I will need to do, I will need to define certain class of bad functionals. Okay, because the bound is about supremum of minimax risk. So I have to find which functional are least favorable for this estimation problem, for which I can hope that the lower bound will be attained. Okay, so I need to come up with some bad functionals. So first, this is already what we discussed. I can, in a small neighborhood, we are working only in a small neighborhood of sigma naught in a neighborhood U. We can choose, actually all operators in this neighborhood will have top eigenvalue also of multiplicity 1. The neighborhood is small, right? So we multiplicity 1, so there is an eigenvector defined up to sign. Okay, up to sign basically, right? So there is, since it's not multiple eigenvalue, simple eigenvalue, and we will always agree that we will choose the sign of theta of sigma, right? This top eigenvector, right? Of sigma in the neighborhood, we will choose it in such a way that the inner product with vector u, right, which is the top eigenvector of sigma naught, will be non-negative, right? If we do this, then this theta of sigma will depend smoothly, okay? Will depend smoothly in the neighborhood of on sigma, okay? It will be a smooth function of sigma. And basically, we will construct least favorable functional. We will need d of them that are of this form. Fk of sigma will be equal to some function hk, which will be defined on Hilbert space itself, right, or on Rd, right? Some function hk, some bad function, right, of theta of sigma, right? And then, as long as these functionals have finite Hölder norms, right, we will create kind of Hölder smooth functional this way, for which will be in correct class, right, for which weighted Hölder norm will be smaller than 1, okay, will be smaller than 1. And we will try to show that for these functionals, right, we will have this bound, okay. I put here only the second term of the bound, right. We need to do separate argument for the first term, but it's much easier. So I'm concentrating on the hard part, okay? So another part is at the level of exercise for someone who takes a course on non-parametric statistics. Okay, this part is more complicated. Okay. Now, what we do next? Okay, next we have to do some exercise that is typical in the proof of minimax lower bound. We have to create a well-separated subset of unit vectors theta omega that will be eigenvector of certain covariance matrices, top eigenvectors of certain covariance matrices from our neighborhood U. Okay, they will serve this role. Okay. So the way to do it, we can first prove that there exists a subset B of this binary cube minus 1, 1 to the power d of large enough cardinality, larger than say e to the power d over a. And we need also an additional condition on this that U inner product with omega is less than 2, okay? And then the main condition is that Hamming distance between omega and omega prime will be large, okay, larger than d over 4. Hamming distance is always smaller than d, right? So it will be larger than d over 4 for all omega not equal to omega prime. Okay, so kind of well-separated binary vectors in Hamming distance, okay? If I did not have this extra condition, right, and I did not have this extra condition, it would be what is called, one of the versions, what is called Warshamov-Gilbert lemma, used in information theory and used a lot in the various techniques of proving lower bounds, okay, in statistics. Now, then we choose epsilon that will be of the order square root of d over n. D is the dimension that later will become R, okay, effective rank, okay? So basically the dimension of the space in which sigma naught and all other operators will act, okay? Square root of d over n, and then we create certain set of unit vectors, okay, parametrized by omega, okay, parametrized by omega, and they are defined this way. And you can prove that any two vectors with different omega and omega prime, you know, the distance will be basically closely related to the Hamming distance, okay, by this bound. Okay, it will be roughly like epsilon divided by square root of d times square root of the Hamming distance. And from here, it will follow that the distance will be of the order epsilon between any two different vectors, okay? Euclidean distance, right? Usual Hilbert space distance. Okay, so what do we do next with this? We will denote sigma theta, a covariance, spiked covariance for which the top eigenvector is theta, right? Spiked covariance acting in our space L, for which top eigenvector is theta. And then this covariance sigma theta omega will be in our neighborhood. Okay, it's kind of everything is chosen in such a way that these covariances will be in our neighborhood. Then we will start generating Gaussian data by sampling from these covariances, right? From these covariances, and this is the distribution of n Gaussian observations, right? This is the distribution of n Gaussian observations, and if you compare this distribution for different omega and omega prime, right? There will be an upper bound on this Kullback-Leibler distance, right? So there will be close in Kullback-Leibler distance, and this will be smaller than logarithm of cardinality of B, and this is because we choose epsilon square as d over n. And this is of the order d, okay? This is of the order d since B was a large set, e to the power d more or less, right? This was cardinality of set B. And this is a kind of well-known fact in statistics that then you could not estimate parameter itself, right? In this now discrete model with discrete parameter space, minimax risk could not be better now than epsilon square. Okay, you can from these facts you can derive this. Okay, now this will be the main part actually of this, okay? This is what was in some idea in Arkadiy's paper that we will exploit, okay? We will construct certain functions now of theta. Theta is in our Hilbert space that are kind of bump functions, okay? They are sums of bumps. Bump is will be kind of small bumps. Bump will be a function either positive or negative. Either positive, we go positive bump or negative bump, depending on whether omega k is +1 or -1, right? Depending on whether omega +1 and -1, and the bumps are around this point theta omega, and the supports of this bump function, they have finite support. They are supported in a small bolus actually after this rescaling, and supports of this bump functions are disjoint, okay? Are disjoint, are even well separated by distance of the order epsilon again, okay? And this fact that they are disjoint allows us to see that the Hölder norm, right, of this thing will be smaller than 1. It's actually also related to the fact that we put here epsilon to the power s. Okay, when we differentiate, we will get epsilon to the power s -1 in the first, and so on and so forth. But we are not going to go down to 0. Okay, in this case, so we will preserve even Hölder smoothness. Okay, in this case, so we can prove that this is the case. And this is very important observation here, that if you compute, it's immediate, that if you compute the value of this functionals at theta omega, right, at theta omega, then thank you. It will be equal to this thing, right? It will be equal to this thing. And what it tells us that the values of functionals hk, k from 1 to d, right? They're defined from k equal 1 to d. The values of functional hk at theta omega allows us to recover coding of theta omega, right? Allow us to recover omega, right? By looking at the signs, okay, of these things, right? We will know what is omega. These are some small values because epsilon is small, epsilon to the power s is small, but it's either positive or negative, right? Depending on what the sign. So if we know this, these values of the functionals, we know also the, okay? Now, how this is used, okay, how this observation is used. You can also show that there are, that you can now kind of, instead of looking at functionals of, on the vector space itself, on the Hilbert space, you can start applying this to covariances, right? And we can create this functionals fk of sigma omega, fk of sigma, which will be hk of theta of sigma. Right? And these functionals will be again Hölder smooth, and again will possess this property by looking at the values of this functional at sigma theta omega, we can recover omega, right? We can recover omega. And moreover, you can see that if you introduce certain distance between omega and omega prime in terms of the values of this functional, this distance will be up to this factor, okay, up to this factor equivalent to the square of the Euclidean distance, okay, to the square of the Euclidean distance. And then it becomes natural what is happening on the next slide. Also, you know, there are some little details here that if you can create, right, if you can create estimators of all these functionals, right, with certain error that is of the order delta, right? That is of the order delta. And we would be able to do it if we choose delta as this max, min, max risk in our problem, right? Because all these functionals belong to the proper Hölder ball, right? And all vectors theta omega belong to where they should belong, and covariances belong to where they should belong, right? So all this is dominated by these quantities that we are trying to bound from below. If we assume that there are estimators of this guy with this property, then you will have also this property. You will have also this property. And from there, you can basically use the values of these estimators to estimate omega for your vector theta omega, right? And create an estimator of theta omega, okay? Create an estimator of theta omega, and then for this estimator, right, for this estimator, using these bounds on the distances that you describe, you will get an upper bound of this order, okay, an upper bound of this order, but we have also a lower bound, minimax lower bound of this order, right? And if you compare this bound, you will figure out that delta should be larger than epsilon to the power s, okay? So the idea basically is that you can use Here you can use functionals, okay, the fact that functionals can be estimated with certain good enough error in order to create estimators of the parameter itself, okay, in this discretized model, right, for which the error will be, controlled by the error that we have for the functional, right? And since we have lower bound in this problem, we can compare the bounds and get the bound on what is possible for estimation of the functional. Okay, that's basically the idea of this argument. Okay, so I kind of will skip this, and maybe we'll just spend the last 5 minutes on a very brief discussion of another problem. Okay, and this problem is about an estimation of what is called trace functional of covariance. Okay, so this is trace of a smooth function applied to sigma, right? Trace of a smooth function applied to sigma. It can be written, of course, in terms of eigenvalues, and it can be written in terms of what can be called the spectral measure of sigma. Okay, so this kind of counting measure on the set of eigenvalues of sigma. Okay, on the set of eigenvalues of sigma. These are important functionals in many problems, and one would want to estimate this for a given smooth function f based on the data the same way as we just estimated other functionals, right, or developed method to estimate other functionals. Now, this functional is not Hölder smooth in the sense that we discussed. If you compute its derivatives, you will see that derivatives can be as large as the effective rank, for instance, okay? Could be compared in size with the effective rank, and effective rank we view it as something large, so it's not in Hölder ball of radius 1. At very least, okay? So the methods that we discussed do not directly apply in this case. Now you can try to use the same thing as we use always, right? At least as a first step. Plug-in estimator. Plug-in estimator has special name in random matrix theory. It's called linear spectral statistics, right? And it has been studied for ages, okay? What is happening with linear spectral statistics, it kind of goes back to the results of Marchenko and Pastor in the 60s, who basically proved that if for instance, we are in this standard framework in random matrix theory, when dimension divided by n converges to some number gamma, then normalized trace functional, right, normalized with dn, which is integral of this kind of normalized spectral measure, will converge to some limit law that is called Marchenko-Pastur law. Okay, they explicitly wrote this law. Okay, so this is in the case when the covariance is identity matrix, right? Is identity matrix, so for standard normal model. But for general model, it is also know what is happening if you have now sigma, which kind of, we are in the framework where dimension grows with n. So sigma is sigma n, say, right? And if you have such sigma for which normalized spectral measure converges weakly to some limit, right? To some limit, then it turns out that normalized spectral functional in this case will converge to this integral. And here we have this limit measure, and this sign means what is called free convolution. Okay, free multiplicative convolution. This is a notion that comes from non-commutative probability. Okay, free multiplicative from free probability. Free multiplicative convolution of measure mu. So there is some operation on measures, convolution type operation. And convolution of this limit measure mu with Marchenko-Pastur law is what we have here in the limit, right? What we have here in the limit. Also people studied Gaussian fluctuation for this thing. So if you subtract from trace function of dn times this integral, right? It calls this process psi n of m, then finite dimensional distributions of this process will converge to some Gaussian process, okay? Now, what it really means, okay? What it really means? It means that, in fact, tau f of sigma n hat, okay, tau f of sigma n hat will be equal to this integral, right, approximately equal in distribution to this integral plus Gaussian noise, which by the way does not tend to zero. It's a finite Gaussian random variable, okay, not small, okay. And then what we want to estimate is this thing. So we want to know something about the spectral measure, essentially, right? About the spectral measure. People tried still to work in this framework and to resolve this problem, but I could wish them good luck, okay? Because this is a terrible problem, because we are dealing with Friede convolution problem, right? Friede convolution problem, and also with large noise, essentially. It's not with small noise, okay? And how to get from there this information becomes complicated. Okay, now on the other hand, there are many simple examples of this problem. This is one of the examples, is the example of what is called a log determinant, okay, which is at the same time trace of logarithm of sigma, okay. And in this case, you can easily figure out that there is a simple bias correction that can be explicitly computed, okay, explicitly computed, and it allows to get the rate of this problem, convergence to the normal, very, very easily. It's easy in this example because it's easy to see that because of some cancellation, this thing here will be equal to log determinant exactly of sample covariance based on standard normal, basically on of Wishart matrix, if you wish, okay, normalized Wishart matrix, okay. And this thing, you know, a lot is known about this thing, and it's equal in distribution to sum of log high square random variables, and you can just do all the computations explicitly in here in order to independent log high square and but so in this case bias correction is trivial, and you can do everything very easily because you can work with standard normal case, okay. In general case it's more complicated, but what I tried to use a bias correction method that we developed, okay, in order to study some problems of estimation of trace functionals, and it turns out that it's doable. And this is one typical result, okay? You can compare it with what we discussed before. Basically, the error rate in this problem will be different, okay? Instead of 1 over square root of n, we have square root of r of sigma divided by n, and it's something that we can expect in this type of problems, actually, right? In the case of some standard normal model, it will be square root of d over n, say, okay? And then here we will have r of sigma multiplied by this. So before we had 1 over square root of n, and we had only this term in Hölder-Smooth case. Now the second term is multiplied by r of sigma, the first term by square root of r of sigma, okay? And you know, because of this, there is a different threshold between fast and slow rates, okay? Different threshold. You can prove, you know, the same type of results that lead to normal approximation and stuff like this. And the last comment here, okay, what is all this based upon, okay? We need to deal in this case with a different notion of smoothness, okay? And smoothness of trace functionals has been studied a lot in the literature. And this is, for instance, you know, kind of well-known formula called Lifshitz-Crane spectral shift formula. Okay, it was discovered first by a well-known theoretical physicist Lifshitz, okay, who wrote on who kind of did this computation a lot in the late 40s, okay, and he published a paper on this in a mathematical journal where he gave his derivation, which was not a mathematical derivation. Basically, what it says that the trace of the difference of this perturbation of f of a, right, of f of a, can be written in terms of certain functions that depends only on operator A and on perturbation. And for any f, it can be written as an integral of f prime of lambda multiplied by this function, which is called spectral shift function, okay? It was proved rigorously by Crane next year after this, okay, was claimed by Lifshitz in a paper that he gave to mathematicians to think about, okay. It was proved by Crane under some assumptions on Fourier transform of function and its derivative, Okay, that were the assumptions in Crane paper. Now, Crane believed that it should be true for any Lipschitz function f, for which the derivative is defined at least almost surely as a result, okay, but happened to be not true, okay. People found counterexample to this. Some assumptions are needed, okay. Then it was kind of developed much further. There was an open problem for a number of years how to do Taylor series in this case, whether there is a sort of higher order version of Lipschitz-Crane theorem, okay? And it turns out that there is a higher order of Lipschitz-Crane theorem. This is a paper published with solution of this problem published in 2013 in Invenciones, okay, that tells that you will have this type of decomposition, right, with higher order spectral shift function under more or less the same assumptions under which Crane proved it, okay, for m equal to 1 for Lipschitz case. And the remainder is controlled in terms of Schatten norm, okay, in terms of Schatten norm. Okay, so this technology, it's also from there you can extract formulas for the derivatives, and stuff like this. So this technology can be used in this framework in order to develop our method, okay? You could not use, it's a bit harder than to get the bound on the bias, under just smoothness assumption of f, because the Taylor expansion holds under stronger assumptions. You need kind of integrability property of all derivatives. But it turns out that you can do it first for such functions and then extend by some approximation argument to all functions, okay? And this leads to this type of results, okay, that I proved. You need also to use different concentration bounds develop in this case and kind of use bounds on Schatten norms because the remainder is controlled in terms of Schatten norm, but it leads to this type of results, okay? So let me stop here because I'm already out of time, sorry.
We would like to thank you for these excellent lectures. They were very well organized on really deep topics, and as a our appreciation, please accept this little gift.
Oh, thank you very much. Yeah, it's heavy. Yeah, thank you.